one of the prints in this unit asks you what units were used on the blueprint. The answer is not metric. Metric is the system. Millimeters are the units. Right? Over here, it says inch system. There is no such thing as the inch system. What is its correct name?
SAE standard. Or
Customary system. The units in the customary system are inches. There's no such thing as the inch system. Inches are the units of measure. Okay? So you've got the metric system and you've got the customary system. You've got millimeters, the units of measure, inches, the units of measure. Okay? Metric dimensions, however, do not show insignificant zeros. So in the inch system, if you've got a really important dimension, you might put a bunch of zeros at the end. What does that do for you? So something changes the tolerances. What tolerances you're supposed to apply to that dimension. If you have 1.50 and then 1.5000, those tolerances are different. In the metric system, they're not going to put those extra zeros. If it's an important dimension, they'll specify that it's an important dimension. They'll put the tolerance right next to it. Right? So you're not going to see insignificant zeros. Also highlight next sentence. Whole millimeters will not include a decimal point. So if your part is 10 millimeters long, they'll just put 10, no decimal point. It's 20, no decimal point. Dimension of less than 1 millimeter will always include the zero. So if the dimension is 0.5 millimeter, you're always going to see the zero in front of the decimal point. Inch system, we'll just put point and then 5. Metric system will always put that zero. So, if you're working with a metric print and you don't have metric inspection tools,
oh man,
you're going to have to do a conversion. The book tells you to multiply it by 0.03937. What is the easier way? Use 25.4. 1 inch equals 25.4
millimeters. Millimeters.
So if you are going to inches and you're converting it to millimeters, you have to multiply by 25.4. 1 inch times 25.4 will give you 25.4 millimeters. If you are going the opposite direction, millimeters to inches, you're going to do the opposite. You're going to divide by 25.4.
what's the difference between the way the book is calculated and using the 25.4?
So if you do, if you put your calculator to 9 decimal places, so more 3 times, and then 1 for fix, and then set it to 9, and then do 1 divided by 25.4, what number does it give you? 0.03937, which is what it has here. But what do you notice at the end? There's still more digits there. So if you're using the one the book tells you, it's not going to be as accurate because you've rounded your number. If you're using 25.4, not only is it easier to remember, you'll always get an accurate answer. So some metric blueprints will include the inch equivalent. So there'll be a little chart on the blueprint. And it'll have inches on one side, millimeters on the other, and all the dimensions will be converted for you.
That's nice of them.
The idea is so that you don't make any stupid mistakes. Only life was that simple. Alternatively, it can be dual dimensions. You'll have both systems together on the same print. So your dimension might be in millimeters, and then you'll have some square parentheses with the inch equivalent to the side of it. So it doesn't matter where you send the blueprint, you're going to be able to read it. Alternatively, you might have it in inches, and then the metric in the square brackets. All depends on where the drawing was created. It was created in Europe, for example, the main units are going to be millimeters, so the inches would be in square brackets. If the blueprint was created here in the US, inches are the main units, metric will be in the brackets. Right?
Do we do that in the U.S., like a U.S. print? Will we have?
You might see it. Any questions so far?
If you get a print and it's entirely in millimeters, would you, before you do anything, would the first step be to take all the conversions and get that first thing?
Depends. What do you have to do to the part? If all you're going to do to the part is drill a hole, why do you need to convert everything?
Oh, yeah.
So it all depends on what you're going to do with the part. If you have to make the whole piece, I would ask the drafter, hey, can you just print this in inches for me? All he has to do is change the mode on the software, on the CAD-CAM,
And it'll do it.
print, and it's done for you.
And then you got to print
But
it.
if the company sent you this print, then you don't have to convert it. So it all depends.
So there wouldn't be a way, say if the company sent you a print and it's all in metric, you couldn't like scan that print into your computer and then convert it through the
I'm
CAD.
sure there's a software that can do it, but is the company going to pay the money for it? Is it really necessary? Do you do enough metric blueprints to warrant paying for that software? When all you got to do is use 25.4 on your calculator.
Yeah.
So if you turn over the page, we've got a list of the most common symbols you're going to see. Should have seen the majority of these by now. diameter, radius. I'm going to come back to these two in a second. Reference dimensions, a line underneath telling you dimension not to scale. X for the number of times or amount of times it's repeated. Arc length. It's not too common, you're going to see that. The dimension will have an arc above it. Right? The length from here to here. If it doesn't have an arc, what is implied? The straight line distance. Right? But why don't we really need that arc length? How would you program that on the machine?
With the radius.
What code?
G3?
G2, because it's going clockwise.
G2, I mean.
You put in the X, Y of where B is located, and then tell the machine where the center of the arc is, using I and J. You don't care how long the arc is, the machine is going to machine it. So that is why it's not common that it's given to you. You don't need it to write your program. All you need to know is where it ends. The machine will figure out how far it needs to move. Underneath arc length, we've got square. So what does this symbol tell me? Part is square. Right? You've got depth, counterbore, countersink, conical taper, and then you've got slope. What is the difference between conical taper and slope?
Well, conical taper goes like this, right?
Conical tapers are generally on round parts that are symmetrical on the center line. So this here is a conical taper. Right? A slope is when that angle is only affecting one feature on one side. So this here is a slope. Right? It's just an angle, an incline. That's all a slope is. And then we have dimension origin, which we'll get to later, and spot face. So what is the difference between spot face and counterbore?
One is deeper than the other one.
One is what?
Deeper.
Kind of, something more to it.
One is designated, like spot face will be a specific, like, is it 30,000s?
Counterbore should always have a depth. Spot face, the depth may not be given.
It's only 30 to 60,000s or something.
30 to 60,000 typically. The idea of a spot face is just to go deep enough so you get a flat surface at the bottom. So when you put the bolt in, it sits on the flat surface. The idea of a counterbore is so that your bolt sits below the surface. You're trying to hide it so something can go over the top and it won't be affected by the bolt. So what is spherical diameter and what is spherical radius? What's the difference between a diameter and a spherical diameter?
Like if you have a screw, right? That's a spherical diameter.
What shape is my pen?
Sphere. It's a sphere. It's a
cylindrical.
It's a circle.
It's round from this view, but from here,
It's spherical.
rectangular. That circle is only two-dimensional. On the spherical diameter, it's three-dimensional,
Like that.
like a ball bearing, or like the Earth itself. It's round all the way. It doesn't matter what direction you go. It's a radius. But on this one, you don't have any radius on this plane. Right? So a spherical diameter and spherical radius are three-dimensional. When you take your measurement, doesn't matter what direction you go, it's round all the way, just like a ball bearing. The normal diameter is only round on two axes. And this is where it gets a little bit more complicated. Metric threads. So first sentence says metric threads are specified on engineering drawings in a system similar to unified threads. So let's do an example together. 7/16 20 U and F to B. Let's change. Coincidentally, these are the bolts that you made in Module 3. The bolts that are going to screw into these clamps once we finish these clamps. So what does the 7/16 represent? The major diameter. The 20 threads per inch. The UN.
It's the class of fit. No, not the class of fit. The series.
The form.
Form.
The shape of
Damn.
the thread. Right? The shape of the thread. Form.
The other one is this. The class of fit is 2.
F is the series. So what is the form trying to tell you? Talked about it earlier. Page 221. What is the form trying to tell you? That's the name of the form, but what is it trying to tell you? Shape of the threads. So again, what is it trying to tell you? Trying to tell you what kind of threading tool you need to use. Could you create a unified national thread using an Acme threading tool?
No.
Right? It's trying to tell you what kind of threading tool you need to use to generate the thread. The shape of your tool has to match the shape of the thread. Okay? So just think about this for a second. You did a 7/16 20 thread on those bolts. What does your threading tool look like? Look at the Unified National Form. What do you see at the bottom of the threads? The radius. Where's the radius at on your tool?
Doesn't have
You don't have one. So how are you creating a unified national thread with a tool that has a sharp point? What you're really creating is what? A sharp V thread. Right? You're not using the right tool to generate those threads. every thread per inch uses a different radius. So you'd have to go back and forth to the grinding room changing the radius all the time. That's why they don't have you put the radius on there. But some of you, your bolts are not going to fit once we start to assemble those clamps. I'll show you how to fix that once we get there. Right? So the UN is telling you what kind of threading tool you need to use.
The form.
The 2
Class of fit.
is the class,
1, 2, 3.
and ARB is whether it's
External,
external or an internal thread.
Internal is B, external is A.
So you were told to make a class 2 thread. How do you know it's class 2?
There's only 3 classes, 1, 2, or 3. So
How did you check it?
with your thread
Took
gauge,
one of those nuts from China and screwed it on, and if it fit, you said it was good. That's your gauge. How do you know that nut is right?
your thread gauge. I mean, is it
You took a nut that you bought. How do you know that nut is the correct size? You don't. So how could you use that as a gauge? What were you supposed to use?
thread gauge?
Thread wise. How much
Oh.
tolerance did you have?
Use your OD mic to measure.
So how could you manufacture those threads if you didn't know what tolerances you had? What you're supposed to do is look up in the Machinery's Handbook here. Right? If you wanted to buy one of these, the latest edition is edition 30. This size is about $80. You can get a bigger one where it's a little easier to read. You can see the size of the writing for about 110. Don't need to, but there is a mountain of information in here. And it has a whole unit regarding threads. So we have that many pages of this book just for threads. And you can see it's got metric threads, unified, acme, buttress, pipe threads, Whitworth threads, any thread you can think of is going to be in here. First few pages show you how the numbers have been generated. Shows you all the trigonometry and the terms. And then it starts to go into some charts. So you're going to look up the thread form that you're working in. In our case, it is UN. So we look for the UN threads. And down this first column, you're going to look for 7/16 20. 7/16 20 is here, right, where my thumb is right. I'm going to pass the book around so you can see it. And then in the next column, you have the class. Class 1, Class 2, Class 3. You follow that across, and it gives you all your tolerances. So as an example, 7/16 20. For Class 2, what is the tolerance on your major diameter?
It'll be in there, right?
It's in here, but what did you make it to?
Plus or minus 1,000.
Did you make it 7/16?
I forget. We made
The thread's wrong. Right? 7/16 20, it's saying the diameter for Class 2 has to be 436 thousandths to 428. That's your tolerance. That's what the major diameter needs to be. It's not 7/16, it's actually a little bit smaller. That allows the clearance for the nut to go on. Right? And then as you go across, you look at the pitch diameter. That gives you the tolerance for your wires. So on the threads, you put in those wires in here, right? and then you put your mic over the top and get a measurement. What you are actually checking is here, the middle, which is called the pitch diameter. So when you look in the book, that gives you the tolerance for your pitch diameter. How much tolerance you got when you use those wires.
And the pitch would be
Right.
kind of like where
It's
that
the
V is.
middle point.
Is that the,
So the major diameter is at the top of the threads. Think of that apex. The minor diameter is at the bottom. The pitch diameter is the exact middle between those two.
oh, okay.
So the major diameter is across the top of this thread against the top of this thread. That's the major. The minor is the bottom of the threads. Pitch diameter is the middle of those two features. Okay. So when you see a thread caller that says class 1, class 2, class 3, you've got to look in that book. It's the only way you can get the tolerances. Unless your company specifically has the gauges already set up. And then you just use the gauges to check. So how does that affect metric threads? The major diameter is listed first, but after the prefix M. M represents what? Metric, which represents the form, the shape of the threads. What kind of threading tool you need to use to generate the threads. The 10 represents the major diameter. In what? In millimeters. We're not using inches anymore, it's millimeters. Then you have the pitch. You can't have threads per inch in the metric system. Why?
The units of measure aren't.
We're not using inches anymore, we're using millimeters. So you can't have TPI. So they use pitch, and you might see a dash, or you might see a multiply sign, followed by the pitch. So what is pitch?
It's that center point between the threads, not the top, not the bottom, but right in the middle.
It's the distance from one thread to the next thread at the exact same position. So if you measure from the top, you've got to measure to the top of the next thread. That is the pitch. If you measure from the bottom, you've got to measure to the bottom of the next thread. It'll be the same number, still a pitch. As long as you measure the same point on this thread and the same point on this thread. Right? The distance from a position on one thread to the exact same position on the next thread.
That's pitch.
That is pitch. The distance from one thread to the next. After that, you're going to have the tolerance class designation. We'll come back to that one in a second. There are only two series in the metric system. Coarse,
Or the other one
the most common,
fine.
and fine.
Fine.
That's it. Coarse and fine. Turn over the page. Have a look at that metric thread table. You've got metric threads all down this left side.
Tap size, drill size, inch equivalent.
From M 1.6 all the way down to M7 by 1. Those are all coarse threads. The fine series doesn't start until you get to 8 millimeters. So once you get to M8, you notice how there's 2 callouts now. There's 2 M8s, 2 M10s, 2 M12s. One is coarse, one is fine. So how do you tell the difference between them? Coarse is always the larger number. Fine is always the smaller number. So you got M8 by 1.25, M8 by 1. Which one is larger? 1.25. So that is the coarse thread. M8 by 1 is smaller, so that is the fine thread. Okay. So the smaller the pitch, the more threads you're going to have. The larger the pitch, the less threads you're going to have. In the next column over, it says drill size, right on. That is the top drill size in millimeters. So somebody call out a thread. Pick a thread on the table.
About the M18 by 2.5.
M18 by 2.5. I'm going to use a 15.5 millimeter top drill.
Correct.
Someone else pick one.
You just need that off the top of your head?
You tell me. Which one? M14 by 2, 12 millimeter drill.
That's the deal.
No, it's right there. It says
Pick one.
And 3.5 by 0.6.
M3 by 0.6.
And
3.5 by
3.5 by 0.6.
Mhm.
2.9 millimeter drill.
correct.
You think I got all these memorized, or there's an easy way to do it?
It's because you went to Oxford.
There's an easy way to do it. Top drill size. You take the major diameter and you minus the pitch. That's it. You don't need the top drill chart. So M10 by 2, 10 minus 2, 8 millimeters.
Does this work for inches as well or no?
Does, but the thing is when you're doing it in inches, you've got to convert that TPI into pitch.
So you're wait.
So unless you can do 1 divided by 28 in your head,
Yeah.
it takes a little bit more work.
So you're subtracting the major
Pitch.
diameter from the
It's subtracting the
pitch from the major
from the major
major
diameter.
diameter. And that's all you're doing.
That's all I'm doing. Very simple. Don't need to go walk across the shop and find the top drill chart, or go to your box to figure out what size drill you need. So on some of them, where you've got like that 7.5, so if you do 4.5 minus 0.75, you don't get 3.7, you get 3.75. Reason being is the increments of the drills go up in 0.1 increments. So you can get pretty much any size drill, 5.1, 5.2, 5.3, 5.4. But if you want a 3.75 drill, you've got to pay more money, it's custom. So people just drop down to the nearest size to drill it out.
Like the M10 by 1.25. I
That
might.
should be 8.75.
Yeah.
But now you've got to buy a custom drill. So they just say, let's just drop down to 8.7.
Oh, okay.
So if you put in your calculator 0.05 and divide by 25.4, how much different is that drill?
20,000
20,000s or 2,000s?
or 2,000.
2,000. Less than the thickness of a piece of paper.
So it's not gonna.
How
be
much difference is that going to make to your thread?
Not a lot.
Virtually nothing. So that's why they just dropped.
So when you see, if you see the difference here, ignore it. Just
It's not going to make a difference. So if you do 6 or any of these numbers and divide it by 25.4, you get the inch equivalent. So these numbers are just that number divided by 25.4. But what's the likelihood of finding a drill 80 thousandths and 7/10 in the shop? It doesn't exist. So these are the next closest size. So some shops will take on some special projects. And the guy might say, okay, I want an M6 by 1 thread. You've got to buy the tap. You've got no choice about that. But you don't necessarily have to buy the tap drill. You can use an inch equivalent, right? So if you were to do an M6 by 1, you should drill it 5 millimeters, which translates to 0.1968 in inches. So if you keep coming across, the number 9 drill is 196 thousandths. How much difference is that? 8 thou.
Oh,
8
8
tenths.
tenths. Yeah.
8 tenths. Virtually no difference. So the guy will just say, use that inch tool and we'll buy the top. And that means they can save some money and make a little bit more profit. Ideally, use the metric tools
If you have them.
if you have them. Some shops are cheap and they'll try to do things the cheapest way they can.
Hope they don't do that at SpaceX.
You'd be surprised. When I worked at Black & Decker, the running joke was no one would ever buy anything made by Black & Decker because they've seen how it's made. But my cousin worked at Flymore, which is pretty much the rival in Europe to Black & Decker. Same thing. I would never buy anything from Flymore because they've seen how it's made. They look at some of the quality where the people just push it through. They don't care. They've got to hit 100 parts an hour. So if they have to spend an extra 5 minutes trying to fix this part, now that production goes down, the boss comes up. What are you doing? Why are you taking so long? Hurry up.
So that's why, like, you have, like, if you bought a Black & Decker drill and there's a problem, they don't question it. Like, oh yeah, no problem, warranty.
Most of the time,
You get a 1
it's
year.
only factored in on the production cost that X percentage is going to be defective.
Damn, that's crazy.
So if you know anyone that works at Ford or any car company, they'll tell you the same thing. Don't buy one of our cars.
You won't hear that at a Porsche Audi dealer.
Yeah, so if any of you get a job there, don't tell me. So let's go back to the previous page and just talk about this last final thing. After the pitch, you are going to get a class designation. In the inch system, or in the customary system, we have how many classes?
2 or 3. 1, 2, 3.
We have three classes. Class 1 is what?
Coarse? No? Fine? Is it fine, extra fine, and coarse, right?
The worst, the loosest, most tolerance. Class 2 is your typical, and then class 3 is almost interference. So what does interference mean?
It's real tight.
It's really tight. You've almost got to force it on there. It's designed to stay on there. Right? So in the metric system, it's actually 6 different classes. Hence why it's a little bit more complicated. So you're going to have numbers and letters following the pitch. The numbers indicate the amount of tolerance permissible. The smaller the number, the smaller the tolerance. So those numbers range from 3 to 9. Why they didn't go 1 to 6, I have no idea. That's the way it is. So 3 represents the best thread, 9 represents the worst thread. But you're going to see 3 common numbers: 4, 6, 8. So in the metric system, class 1 is roughly the number 8 in the metric system. Class 2 is roughly a 6. And class 3 is roughly 4. After the number, you're going to see some letters. Lowercase letters are used for external threads. So you don't see A or B anymore. You're going to see a capital letter or uppercase and a lowercase letter. So lowercase for external, uppercase for internal. And you're going to see 3 letters: E, G, and H. So you're going to see E, G, or H. So what does that mean to you when you're trying to machine this thread? What are you supposed to do if you do a class 2 thread?
The smaller letter indicates less allowance.
It's supposed to go to that buck that I passed around and look up how much tolerance you've got. So if you get a metric thread that says 4H, you look at that buck, you look for the thread size with 4H, and you see how much tolerance you've got. That's it. It's up to the engineer to design this, what kind of thread he wants. That's not your concern.
So,
Your concern is how much tolerance do you have?
so what does the lowercase and the uppercase have to do with it?
External or internal?
Oh, that's it. That's all.
That's it. They don't put A or B at the end. They just use internal or external. So I showed you earlier this part. You would look up the metric threads. So here you got basic diameters, class 4, 5, 6, 7, 8, and it gives you the tolerances, right?
ANSI, standard pitch diameter.
So that tolerance class designation just means you gotta look at the book and look up those numbers and letters, just like you're supposed to for inch system with the 2A or the 2B or the 1A, 1B. So on the next page, just highlight this part. That's 6H, 6G is the equivalent, or rough equivalent, to a 2A or 2B. And the 4H, 5H or 4H, 6H is similar to class 3.
So they're interchangeable almost?
That can change depending on application. So if you're doing aerospace, you're going to be at the tighter end. If you're doing stuff for like a caterpillar digger that's going to be in the field, you want a loose thread because if there's dirt in there, you still want that bolt and nut to be able to be assembled out in the field. So it all depends on the application. I will be absolutely amazed if you make anything other than a 6G thread.
Why?
99% of the time, it's just called out 6G.
Why is that?
It's the most common, similar to a class 2.
So
It's the most common used tolerance application.
class 2 is just for most industry because it's kind of like in the middle. Not too much this way, not too much that way.
You get a good assembly, and it's cheaper to make.
Cheaper to make.
If you want a class 3, it's going to take you longer to hit those tolerances consistently. So it's going to cost you more money to make the part because you have to sell it for more.
So who would make a class 3? Like SpaceX maybe? But no.
You can still get class 3s made in China, it's just more expensive. Would I trust it? I don't know. Depends on the company. It's like when you go on Amazon and you look at the quality of some things, where did they cut the corners? Most of the time they cut the corners on quality control. And they just ship the part, so it's not 100% guaranteed. It's going to work like you expect it to.
What industry do you think would be where everything is quality control is extremely high?
I mean, it depends, but mostly aerospace and government contracts.
Yeah.
It's not so much that you have to consistently check every single part. It is the documentation that you have to keep.
People can die.
Yeah.
So, I mean, as an example, if you make some titanium screws and they're going to be attached to some feature on a helicopter, how many helicopters did you make screws for? If one of them crashes and they do a report and they say that screw failed, they need the documentation to see which other helicopters they need to ground.
So they can replace all those.
So they replace the screws and then find that company for whatever reason.
Wrongful death lawsuit.
Kobe's helicopter.
Yeah. Well, that was the
So let's have a look at this first print. A couple of things we need to talk about, which will help you on your homework this week.
Millimeters.
This one?
So in the bottom right, we have a note. What does the note tell us?
No, all dims in all dimensions in millimeter.
All the dimensions are in millimeters. We have two views. What are those two views?
Top view and left side view.
Front
Oh,
view
front and left. And then
and to the
oh,
right of that is the right side view. What kind of section view is it?
full section.
Full section. How do you know what's a full section?
There's no broken lines. There's no broken out lines.
Section lines go through the whole piece. What is the purpose of giving you this section view? To show you all the important features, such as these holes. So you can see on the back, in this view, what do you see? Hidden detail. So it's trying to show you what that hidden detail is. Showing you this here. What is this? The keyword. Right? trying to show you all the important features. So question 1, are the units of measurement inches, millimeters, or centimeters? Millimeters.
Millimeters.
Number 2, is the section view half section or full section? Full section. Number 3, what tolerance applies to the flange diameter? So what is the flange?
The point where they
Not sure of a word, where are you going to look?
glossary of terms.
Unit number 1, dictionary of terms.
Is it
What does it tell you about flange? While you're there, look up hub.
A projecting rim or collar on an object? It may include mounting holes to secure it in place.
Projecting rim or collar, which is this feature here. This is our flange. This section here is the hub. What does it say about a hub?
Hub is the central part of a wheel, such as the part into which the spokes are inserted.
Central piece. Right? So what tolerance applies to the flange diameter? What tolerance applies to this number? Where do we need to look? Title block.
Title block.
Unspecified.
So what is your tolerance?
Plus or minus.
Plus or minus what?
1 millimeter.
Why 1?
Because it's not a machine surface.
Why is it not a machine surface?
Not specified.
How is it not specified?
Simple.
Because no finish symbols on the diameter. So down here we have finished dimensions and unfinished dimensions. So because we have no finish symbol, we have to use the unfinished tolerances. Right? See on this face, we've got a finish symbol. That means you need to machine it. On this one, we've also got a finish symbol. Means you have to machine it. But there is nothing on the diameter. So you have to use plus or minus 1. Right? So your answer is plus or minus 1 millimeter. Number 4, what is the maximum material condition of the bore diameter? So what is the bore?
Hole in the center.
Hole through the middle. Generally, bores have a tight tolerance. MMC, maximum material condition. What does that mean about your hole?
The biggest it could be.
The
Or the
smallest.
smallest
it can
it could be.
be. Think of weight. How would you make the part heavier?
Leave
You make the
material.
hole smaller,
Leave more
it makes
material.
the part heavier. So what's the smallest that dimension can be?
25.4.
25.4 millimeters.
1 inch.
Number 5, write the bore diameter, write the flange diameter in limit form. So what's the limit?
Minimum and maximum.
Limit equals minimum and maximum. You always write the maximum at the top, the minimum underneath. So we're going to take the 100 and the tolerance of plus or minus 1. So 100 plus 1 is 101. 100 minus 1, 99. Number 6. Write the bore diameter with an equal bilateral tolerance. So what do we need to do for that one? Find the mean.
Add them both together and
Add them
divide.
both together, divide by 2. 25.45. Equal bilateral means you have a plus and negative of the same number. And that number is 0.05. Remember, in metric, you have to write the 0 before the decimal point.
Right. 'Cause that's not going to be 50 thousandths.
50 thousandths, 0.05 millimeters. Number 7, convert the flange diameter to its inch equivalent. So what are you going to do with 100?
By 25.4. Divide by 20.
Millimeters to inches means divide by 25.4. Number 8, what is the diameter of the bolt circle? So what is the bolt circle?
The middle part is 82.6.
Bolt circle is this center line that all the holes are placed on. Its diameter is 82.6. What is the diameter of the spot face? What symbol are we looking for? The bore symbol with the SF in it indicates spot face, and the diameter of it is 19 millimeters.
And there's a depth call out on it too, though, right? Because normally, if not,
Normally, it doesn't have one.
because it would be 30 to 60.
There's a lot of inconsistencies in this part. Number 10, does the spot face run tangent with the diameter? So what does tangent mean?
The highest point where a
Does
straight
it
line.
touch at how many positions? One position. So does it touch at one position here, or does it touch at 2? We need to calculate, we need to prove it. You can't just say yes or no. So what do we know about the flange diameter? It's 100. So how far would it be from the center? Be a radius, 50, right? What do we know about the bolt circle? 82.6. So from the middle to that edge would be 41.3, half of that. What do we know about the diameter of the counterbore or the spot face?
It's 19
It's
millimeters.
19. So from the middle to the edge would be 9.5. So what do you get when you add 41.3 and 9.5 together?
50.8.
50.8. Are those two numbers the same?
No.
So is it tangent?
No.
No. They have to be the same for it to be tangent. So the answer is no. There is a 0.8 millimeter difference. Number 11. What is the pitch of the threads? Sorry. What is the major diameter of the threads?
10.
Major diameter is 10 millimeters. What is the pitch of the threads?
1.5 millimeters.
1.5 millimeters. What is the tolerance class? 6H. That's it. Are the threads coarse or fine? Look at the table on page 261. So you're going to look at M10 threads. M10 by 1.5 and M10 by 1.25. Coarse threads are always the largest number. So which one is the coarse thread? M10 by 1.5, which is what we have on our call out. So is it coarse or is it fine? Coarse. 15. How many full threads will the tapped hole contain? So how do you calculate this in the inch system? How do we calculate how many threads? Take the depth or the length of threads and we multiply by threads per inch. But in the metric system, there is no threads per inch. So that formula is not going to work for you. So in the metric system, we take the depth or the length and you divide by the pitch. So in the inch system, you multiply by threads per inch. Metric, divide by the pitch. So how much material is threaded? What does this hidden line represent? Follow it across. Have 60. And this section is the whole. What are we going to do with that number?
Subtract.
Let's subtract the two numbers and then what? Divided by 2. It's a wall thickness. That gives you two sides. We only want one side. 60 minus 25.5.
16.
Divide that by 2. And divide by the pitch. What is the pitch?
Distance from one
One
thread
to
to
the
the other
next,
thread.
which is 1.5. That gives us 11.5 threads. So how many full threads is that?
Yeah.
11 full threads.
Would it be so instead of saying TPI, would you be like TPM, or do they do that? They don't.
Exists.
Doesn't exist. Just it'll say full threads.
All it's going to give you is pitch.
Oh yeah.
So, any questions about what we covered today? What does the M represent? Don't say metric. Form. What shape the thread is going to be. 10. Major diameter. 1.5.
Pitch,
The pitch. 6H.
class.
The class. Very similar to the inch system. Just have the M at the front instead of the UN after the numbers. Anyone taking a look at the homework for the week? No. Why would we do that? So take a look at it over the weekend, and then I'll answer any questions next week. What I want you to do is pull out that blueprint that I gave you yesterday. This is very similar to the one you did as a pen plot, except this one we are going to machine. We're going to take that 3-inch by 3-inch piece that we cut the side the other day, and we're going to machine this engraving on the top of it. To do that, we're going to use a 1/8 ball end mill. What do we know about the material that you have?
It's aluminum.
It's aluminum. What else?
The dimensions. It's
It's
thin.
3 by 3, 1/4 inch. But what do you know about this surface here?
Unfinished.
It's unfinished. Is it flat?
No.
No. So if you try to engrave on the top, certain parts will be deeper than others because it's not flat. So what do we need to do before we engrave it?
Finish it.
We're going to fly cut across the top to make sure it's flat. Then when we do the engraving, it'll be the same depth all the way around.